Welcome to our NPTEL courses on the power quality improvement technique. Today we shall discuss this last part of this PWM converter, and it will be discussing one important topic, that is SHE. So, one of the problem of the sine triangle and the SPWM is that higher switching frequency, and thus it has a huge switching losses. So, every switching period it will turn on and turn off. So, of course, it is switching on and off in 2000 time or 20,000 time, depending on the switching frequency. Another issue is that with a higher power rating, we require to reduce the switching frequency. For the example, GTO is operated below the 1000 kilohertz, and this method is preferred method mostly in GTO or thyristors having the commutations involved. So, in this way what happened, we try to, we have discussed the square wave inverter and its THT and other problem. So, we know that if it is C phase 3 wave system, what are its the content of the harmonics, and how it is one of the method to reduce this harmonic. We have discussed in detail that what are the effect of the harmonics. So, we are not going to that detail, we are discussing that it can be eliminated from its stage of beginning. So, that is all it is. By placing notches in the output waveform, these are the notch 1, notch 2, notch 3, and ultimately these are the fundamental. It is just like you play a guitar and you touch by hand or the metallic bar, and there you create a note. Same way that when you create a note, so a particular harmonic will be eliminated from the system, and thus you generate a particular tune. Same way you can particularly eliminate your unwanted harmonic here. In the output waveform at the proper location, certain harmonic can be eliminated. Generally what happen, if you see fifth harmonic is a form with respect to sixth harmonic is a cophasor. Since third harmonic is a cophasor, sixth harmonic and multiple are the cophasor. With respect to sixth harmonic, your fifth harmonic is a negative sequence harmonic and the seventh harmonic is a positive sequence harmonic. So, if you have a fifth harmonic, you are going to generate a ripple, torque ripple in a for the negative sequence. So, that is quite hazardous, and for the motor drive. And also if it propagates, I will show you the how does it propagates and all. So, this will be causing damage to the motor, and thus it is better once you are applying for the adjustable pit drive and other method, you eliminate this at the very beginning. This allows the lower switching frequencies to be used and also lower losses, because there is a less switching losses, and that gives you the higher efficiency. So, we have a general expressions of the Fourier series we are revisiting here. So, it can be voltage or current. So, that will be given by A n cos n omega t plus B n sin omega n t, n equal to 1 to infinity. So, where A n equal to 1 by pi 0 to 2 pi B I or V t cos n omega t dt. Similarly, B n is the sine component, and where it will be 1 by pi 0 to 2 pi V t or I t sin n omega d dt. For a waveform, generally we have a waveform with a quarter symmetry, and it does not have a DC value, only the odd harmonics with the sign component will appear, and that means A n equal to 0, thus V t equal to 1 into n equal to 1 to infinity B n sin omega t, where B n equal to pi, that is a square average value of it, that is 4 by pi 0 to 2 pi V t or I t sin omega sin n omega t dt. So, we can rewrite this equation. It can be shown that B n will be 4 by n pi, where n is the order of the harmonic. If it is n equal to 3, then it will be 3. So, plus k equal to 1 to k to the power minus k cos n omega t. So, you can see that 5th and 7th will have a minus value here, and thus we can choose k variable, that means alpha 1, alpha 2, alpha 3, alpha k, and we need k by solving the simultaneous equation, because cos is involved. So, you cannot have a algebraic equation. The computer can solve this online, and thus we get the values with k alpha angle, k minus 1 harmonic can be removed from this system. So, you can see that. So, in that way a particular harmonic can be eliminated. Ultimately, you have to make this term cannot be 0, that what happens, you require to make this term 0 by particular value of alpha. Thus, you solve it, you just put this value, consider that 5th and 7th harmonic. We have considered a 3-phase 3-wire system, and thus 3rd harmonic can be eliminated or ignored. A machine has a if the machine has a isolated neutral. So, thus k equal to 3, and the equation can be rewritten. If it is a fundamental, then you write it the fundamental, just expand the previous equations like this. Similarly, this has to be maximum rather. So, this should not be 0, and that will be max, and V 5 will be n equal to 5, this will be 5, this will be 5, this will be 5. Similarly, the 7th, this will be 7, this will be 7, this will be 7, this will be 7, and these are the 3 simultaneous equations required to be solved. So, while solving, what happened, this is a transcendental equations and can be solved by the numerical values having a notch angle, but once if load is fixed, this angle. If load changes, then you require to again readjust angle, but you can see that this is a static value. So, once you know the zero crossing, you can change this value. Generally what happens, load pattern if changes, then power factor changes. So, your angle you have to recalculate with the voltage. So, for specified fundamentals amplitude, for example, if fundamental with a voltage is 50%, that means B 1 equal to 0.5, and thus your alpha values are it is alpha equal to alpha 1 equal to 20.9, alpha 2 equal to 35.8, and alpha 3 equal to 51.2. This approach usually implemented by the microcomputers, DSP, or with the lookup table with angle of the notches, because once it is done, it is fixed, but generally power factor changes and all those things, you require to recalculate those angle, because this value will change, it is not fixed value. We generally want to maximize this value. and see that this is a representation of the triggering angle alpha and the fundamental value of alpha. So, generally what happen, you can see that, so for alpha 1 you gradually increase the alpha 1 and try to reduce it. You can see that what happen, this is the 13th harmonic. 13th harmonic will be initially high, gradually it will come down here and thereafter will increase. So, similarly this is for the alpha 3 and this is for the alpha 2 and this is the 11 harmonic. So, 11 harmonic you will have this kind of pattern. So, thus this is the way, and this what happened, the notch angle relation is the fundamental voltage of 5th and 7, it has been already eliminated. So, you are left with 11 and 13. If you change this firing angle alpha, so this will be the next harmonic will be arises at 11 and 13 and that will be, that has been represented here. Of course, you can eliminate 11 and 13. So, why we require to eliminate, and generally it will propagate, we shall see that if it is adjustable speed type. The flux and the torque output of a motor is directly controlled by the current input of the motor. Thus, having the current control on the output voltage of a voltage fed converter with voltage control PWM is quite important. So, this is something we require to know. A feedback current loop is used to control the machine's current. So, we require to have a control PWM. And generally what we do, same thing can be extended to the shunt active power filter. And so, the PWM technique for the current control is been considered, and it can be instantaneous current control or the hysteresis band. This hysteresis band is very much used in case of the shunt active power filter. So, what happened? This is a instantaneous current control. So, in this case you have a reference sine wave and generally you will start with a delay because you cannot start. So, you have to match it. So, this current will be compared here and ultimately since you have started with a delay. So, you got a effective history and thus you got a steady state error and you require to eliminate the steady state error, and for this reason we require to design this PI controller. This PI controller will be giving you this kind of reference and ultimately you will put it to the simple op amp for its sine triangle comparisons and that will give you the pulses for the PWM. It can be bipolar or unipolar, which has been discussed earlier, and this is the control block diagram of the instantaneous sine triangle PWM with a closed loop control. So, this can also be used for shunt active power filter. You know that shunt active power filter reference is something like this. So, this is the harmonic part of it and we require to track it, and this is the way it can generate pulses for the shunt active power filter. So, what we can say here, this actual current I or I of t, because this is in time domain, is bounded is commanded and the commanded current I star of t and the error is fed to the PI controller. The rest of the circuit is the standard PWM topology. Although this control approach is simple, this method produces a significant phase lag, because we can start correction nectar take place little bit lagging. Ultimately, PI is challenged to get rid of this phase lag business. So, we require to design the P lag properly at high frequency, which are very harmful to high performance of the drive. It generates the ripples and thus ripple in the torque will be presented. And now let us come to the hysteresis band. It is quite important. Hysteresis band is very frequently students use for the simulations of the D-STATCOM or the shunt active power filter. It has a many version. Let us try to capitulate some aspects of the hysteresis band of controller in this class. In hysteresis band, this is all the current control technique. The current control, the actual current tracks the commanded current within a hysteresis band. This hysteresis band can be proportional band or it can be a algebraic band, or you can have a constant band. In this approach, a sign reference current is commanded to the actual phase current waveform. We shall see it, what does it mean by that. As the current exceeds prescribed hysteresis band, the upper switch of the bridge is turned off and the lower switch is turned on. Within a band, it continues to allow to turn on the lower switch. Again, when it goes to hit the lower band, then again upper switch will be turned on. As the current goes below the hysteresis band, the opposite switching takes place. So, this is the case. You start from here, you allow the error to be increased and thus you have this band is called 2 HP band, and this is the middle is the actual value. With actual value you add up some voltage and thus you generate this and this band. This band is said to be the constant band. So, its bandwidth remains constant throughout. So, what happen here? So, you allow to at this point you go off, and since upper switch is on, so current will increase in a positive half cycle and thus it will hit, ultimately upper switch will be closed. Generally it gets a path through the diode to flow and it will come down. And then again when it will hit this lower band, again this diode will be stopped or switch will be stopped, because you require to give a switch to give the path. Your switch is on, then lower switch will be on. For this reason, for this time you are getting the value of minus VDC or 0.5 VDC for the half bridge. So, again you will go off for the switching on the upper switch and go down like this. So, you can generate the precision by controlling the band, but one of the disadvantage of this is that it is nothing but a PWM. You can see that you have a maximum bandwidth at the center and you have a notches very small bandwidth at the close of this device of this zero crossing. So, in that way we can say that it mimics the PWM, but there are some difference. Generally what happen, we consider a shunt active power filter. This discussion is based on the shunt active power filter. I just take an example of the shunt active power filter where you have this point is called PCC. This is a one line diagram of the shunt active power filter, and this one is your diode bridge rectifier and filling maybe a load, and here you have shunt active power filter and you have this load. So, what happen, once this switch is on, this pole of the voltage says VDC by 2 or VDC depending on the kind of topology it is using, and this point it is varying sinusoidally. So, this point will be Vm minus T and you require to inject current, and this value, since there is an instantaneous difference between this point and the pole of the inverter and the PCC, we require to use the inductor, and thus it is been shown here. So, it is LdIdt equal to 0.5 Vd minus Vcm sin omega t by L, where this 0.5 Vd is the applied voltage and V sin omega t is the opposing counter EMF for the motor, or maybe it is connected to the PCC, that the PCC voltage, and it is L is an effective, or you have connected the inductor. Similarly, the lower switch closed, the negative current slope given by this term will be negative minus 0.5 Vd minus Vcm sin omega t by L. So, what happened here? Peak to peak current ripple and the switching frequency are related to the hysteresis band. If you have a larger band, so you have higher, you have a lower switching. So, select the width of the hysteresis band optimally to balance the harmonic ripple and the switching loss. So, if you have more band, harmonic ripple will be more, but switching losses will be less because you are switching less. So, you have to optimize it. And another problem is that in case of this sine triangle PWM, your frequency is constant. You know that where your bandwidth of the frequency will exist for the bipolar and unipolar, but here you have a spectrum and that is not at all, that will have a wide range of variation with a change of the band. And but one of the major advantage of this method is that current tracking is easy at low speed, but high speed when counter EMF is high, current tracking can be more difficult. Let us understand what this says. So, let us switch over. Ultimately, LdIdt equal to your VDC by 2 minus Vm sin omega t. So, what happened? Value of the inductor is constant. So, you can write di by dt. So, this is approximated VDC by 2 minus V sin omega t by L. Now, what happened here? You can see that this is a band that is constant. So, it is at its peak. So, what happened? This value required to be quite high and the frequency required to be high, because you can just change it to the frequency, just inverse of it. Thus, the change of frequency into del I equal to VDC minus d sin omega t by L. This one is constant, thus there will be a change in frequency. There is a constant change in frequency in the operation of this PWM inverter. So, that is what it is. When PWM high, then switching frequency will be high, and the current tracking is more difficult because it does not get much time to operate, because once you are switching on, you have to track it. So, here since there is a peak value, so current will gradually will operate. The slope is quite blunt here, and slope at the zero crossing quite sharp here. And generally what happen, if you are working in the shunt active power filter, you will find notches here. Generally the student do the proportional band hysteresis controller, that is this PWM. So, this one is your proportional band. So, here it will be 0 like this and 0 like this. So, if it is a proportional band, here you have a space, and here since you have a very notch kind of thing, so its frequency required to be higher, and thus control fails, and you generally there will be a overshoot or spikes will be there in case of the zero crossing. That is very frequently observed the students working on the shunt active power filter simulation, because they go for this because it is for this proportional band hysteresis controller. It is always advisable go for the constant band PWM hysteresis band. So, how you implement it? We have implemented everything by op amp, thus it is also possible to implement it by op amp. So, it is a simple control block. So, once op amp with a positive feedback, you have studied maybe your second year of the BTech, that op amp with a positive feedback acts as a hysteresis controller. So, same thing, you will have a positive feedback, and R and R2 will be the ratios of the band which you want to set. It may be 1K, it can be 10K. So, it may be that is 10% band. Similarly, you can have a 5%, 1%, whatever the band you want, but generally this is a proportional band minded. So, we require to have some kind of modifications which is left to the student. I will be asking this question to your assignments, because you require to revise the op amp. So, there you will get a algebraic band, not a constant band, and thus the simple controller will work. So, you have a lockout time, within that no switching will be no changes will be allowed to generate it. If it is high, then higher IGBT will be switched on. If it is low, then lower IGBT will be switched on. So, it is a perfect match for the 3-phase 4-wire system, where individual phase can be run like this, and for this reason this mode of operation is highly preferred in case of the shunt active power filter. So, it is a simple and it is highly useful, but one of the challenge is that we shall see that how to design the inductor of the shunt active power filter. So, there you will be finding that this inductor design is quite challenging because of the hysteresis band. So, there is no constant frequency and you have been challenged for it. So, otherwise this works quite simple and fast. So, as I told you that the error control loop is essentially a Schmidt-Trigger circuit with the hysteresis band HB equal to V R2 by R1 plus R2. When I reference is more than this I, then upper switch will be on and just reverse will happen. Once this one is less, then lower switch will be on, and that will say higher band, and this is high and this will be low. So, these transitions will takes place. So, this hysteresis band is very popular because of the simple way of implementing it, and fast transient response, direct limiting the device peak current, and practical insensitivity of the decelerating voltage ripple. So, these are the few advantage of this hysteresis controller. However, that is a major challenge. PWM frequency is not constant, which leads to the non-optimal harmonic ripple in the machine current as well as shunt active power filter, and can be overcome by the adaptive hysteresis band. So, that band itself changes once there is a big current, big error, band will be higher, so that you can ramp on, and if the error is minimized, so you can have a shorter ramp. So, also significant phase lag at the frequency, because you start with the lag and there is no lag compensator, because history will be prevail, and thus you will have a steady state error. And drawbacks of these methods are, these are the quite drawbacks of the high frequency devices, and it leads to the time delay system also. Thank you for your attention. We have completed in detail the applications of the PWM and voltage source inverter that is very frequently used for the different power electronics devices for compensating or mitigating the harmonics as well as total power quality control, and these lectures will be useful for them for UPQC, STATCOM, DVR, anything, any devices. So, all employs this kind of PWM technique. Thank you so much.